In this video, we want to talk about infinite limits. In other words, limits at infinity as we grow, way out to infinity. What happens? So, if we consider here this polynomial x to the third minus 5x squared, and we start to try to use our limit properties and distribute the limit through, we get as x goes to infinity, x to the third is going to go to infinity. Right? Because if you take infinity to a power, it's still going to be infinity. And then 5 is just the number, but x squared is going to go to infinity. 5 times infinity would still just be infinity. So now we have infinity minus infinity, and we're like, well, what? Is that 0? And it turns out, no, it's not 0. So because limits involving infinity minus infinity are what we call an indeterminate limit, much like our 0 divided by 0 limits were, and much like some limits we're going to talk about in a little while, which involve infinity divided by infinity. Okay. Those are all examples of what are called indeterminate, meaning it depends. That limit might not exist. It might be infinity. It might be 0. It might be a number, some other number. We really don't know. Just direct evaluation on its own is not enough to talk about it or to work it out. Now, if you eventually go on to take Calculus 2, you'll learn about a result called L'Hopital's rule. You'll be studying a lot of different indeterminate forms. Turns out there's 7 of them in total, things that are indeterminate. So the actual thing can't be evaluated directly, but it could still have a limit. So how do we handle this? Well, there's a key idea that underlines most of what we're going to be talking about in this section, and that is this. Let A be any old real number. Let A be any old real number. And let N be a rational number. Right now we're tied to our exponents still being just rational exponents. When we get into what are called transcendental functions, a little later on in the course, towards the end, we'll be able to expand that N to be actually any real number. Okay, so, but let N be a rational number. And now we're going to discuss, how do we handle, this scenario here. So the limit that involves x as it goes to infinity of anything of the form a over a power of x, positive power, well, a is a constant. No matter how big it is, x to the n is going to become an infinitely big. And what's going to happen is that's all going to go to 0. And then when it's defined, the limit as x goes to negative infinity of a over x to the n is also 0. I have to put that precursor in there when defined, is because if x is like a fractional exponent like 1/2, then it's x to the 1/2, which is square root of x, isn't defined for negative values. So we can't talk about a limit there. So when the power of x is defined, the limit as we go to negative infinity is also going to be 0. And what I want to show you is how we can use this idea now to help us work this problem out. X cubed minus 5x squared. So the limit as x goes to infinity of x cubed minus 5x squared. Here's the idea. Let's factor out a power out of all that stuff. And let's specifically factor out x to the third. Let's factor out x to the third. You may think, wait, I can't do x to the third. It's not in everything. Yeah, it's not, but that's okay. We can still do it because when we factor, remember, we are dividing. So if I factor out an x to the third, I just need to go inside and divide x to the third out of each of those pieces. Of course, x to the third divided by x to the third is just 1. 5x squared divided by x to the third would be 5 over x. And so we've now factored out an x to the third. And now we can use our limit properties and say, well, let's do limit of x to the third. What's that going to go to? Well, limit of x to the third is infinity. Let's do limit of the other piece. As x goes to infinity, well, 1's a constant. So that's going to approach 1. 5 over x, that's a number divided by a power of x. And we know that that's going to go to 0. And so we get infinity times 1, which is just infinity. So it turns out the limit of this thing, this infinity minus infinity, actually turned out to be infinity. In fact, in general, this is true. For a polynomial, the leading term, in other words, largest power, dictates the end behavior, because we could always pull that power out, and everything else except for that term is going to involve division by a power of x, and they're all going to go to 0 as x goes to infinity or negative infinity when it's defined. And so therefore the only thing that's going to matter is that leading term, in this case the x cubed times 1. So for a polynomial, the leading term, largest power, dictates the end behavior. That's actually going to be helpful to us as we continue on into some problems where we're dealing with the limits. So let's just look at some quick examples here. Limit as x goes to infinity of 3x minus x cubed plus 5x squared. All that matters is the largest term. So we can say, well, that limit's just going to be the same as the limit as x goes to infinity of negative x to the third. And as x goes to infinity, negative x to the third, well, x to the third will be infinity. The negative sign will make it negative infinity. And then one other example here with a polynomial. Let's look at the limit here as x approaches negative infinity. This time we're looking at 4x squared minus 7x. So again, all that matters is the leading term. So limit as x goes to negative infinity of 4x squared. As x goes to negative infinity, x squared though, so that's going to become positive, times 4 would still be positive infinity. So that's looking at polynomials. We're going to turn our attention to focusing on rational functions and limits involving rational functions. So that's what we're going to turn to next. So till next time.